So you might ask, why do you even need a reranker? You could just use embeddings. Embeddings are given the same exact task. You have a query and a document, and you embed them and take the dot product. And dot products will naturally range between 0 and 1. The issue is the fact that your document gets compressed into an embedding, and that embedding needs to attend to all of the possible queries you could ask about that document. And it's just not possible to be able to compress all of these different combinations into a simple embedding. Hello, I'm Nicholas, the CTO of ZeroEntropy. In this video, I'm going to go over a brief overview for how we trained our state-of-the-art reranker, the ZRank 1. Now first, what is a reranker? A reranker is a model that takes in a query as a string and a document as a string, and it has one simple task, to output a number between 0 and 1. If you're using 1,000 dimensions, maybe even 3,000 or 4,000 dimensions, there are so many different queries that you could ask, and also for a given query, there are so many different documents that could have the answer. Embeddings are great for clustering, so you can even test this. If you take a query, send it into an embedding, a vector database, and try to get relevant results, you'll get all of the documents that are somewhat relevant, but they're going to be very poorly sorted. For example, consider the query, who won the Nobel Prize in Physics in 2017. Then consider these 3 documents. With a pure cosine similarity using OpenAI text embeddings, you'll notice that all 3 documents have a score between 53% and 63%, and it's pretty random. The second one ended up getting the highest score, surprisingly. That means that essentially we found the cluster where most of the relevant documents are located, and this is why with embeddings only, your query is just going to get in there and get the cluster of documents that are around that region. It's not going to be sorted in exactly the way that you want them to, the way an LLM could sort them if it was given the query and the document at the same time. Now, with a reranker, each query document pair is going to be assigned a new relevance score. For example, the last document, which contains the right answer, gets a score of 94% with ZeroEntropy's latest reranker, ZRank 2. The intuition is easier to understand in one dimension. If we could only use one dimension to embed these 4 sentences, we would immediately have a major recall problem at just k equals 2. It would be very easy to retrieve who likes apples because the blue and yellow vectors are next to each other. Similarly, who likes rabbits is straightforward because the red and green vectors are close to each other. However, the moment that both of these are true, it's now impossible to retrieve exactly the blue and red vectors at k equals 2. The same thing happens in higher dimensions, where given a certain k, the retrieval of documents in perfect order becomes very hard or even impossible. In order to solve collecting the blue and red vectors, the only solution in this one-dimensional embedding example is to first do an embedding query with k equals 3, which selects blue, yellow, and red, then use a reranker, which will boost red and blue to the top and leave yellow at the bottom. So you might think that any retrieval problem just needs a simple reranker that anybody could train. Even though the task is simple, getting it to work is very difficult. When we started to train our reranker, we looked at the existing state-of-the-art methods, and one of the most common methods is Triplet-Loss, where you take in a query and you have a known document where the model should output 1, and you have a known negative document where the model should output 0. And you can train your model to essentially predict whether or not it should output 0 or 1. Even though you've only trained it on 0 and 1s, when you actually go ahead and inference the model, you'll often get a number like 0.7. That means the model is 70% sure that the document should have gotten a 1 instead of a 0. When we were working towards training rerankers using this method, there was a very strong limit into how good it could be, and it really depends on that negative document. If you look at datasets, people will annotate positive examples of query, document pairs. Consider that Nobel Prize query again. If we're searching over Wikipedia, then we would want the human annotating that this document is a positive example because it contains the right answer. Then we can use that positive data point in our training pipeline. But where do you get the negative from? As we saw before, for Triplet-Loss, we need a positive and a negative document. The positives come from these human annotations, but finding a good negative sample is not easy, and here's why. One way is to randomly sample documents out of a large corpus. Presumably, it's less relevant than the known positive. The issue is that the negative document here is way too obvious. For example, if I take a random Wikipedia article as the negative, that article is very likely to be extremely irrelevant and not useful. For example, this triplet is not going to teach the reranker anything because it's just too obvious. The reranker will learn it quickly. It's obviously not relevant at all to the question. So while the model is capable of learning which one's more relevant, it's not capable of being very intelligent or making difficult decisions, such as when the documents are potentially similar. So we tried to make the negative stronger and stronger, and we even built full agentic pipelines to find the hardest possible negative. And when we did that, the models would get better and better and better to a point. and then they quickly started to get worse. This may seem like a surprising result. The intelligence of the hard negative miner starts to help in the beginning, and then after that it begins to degrade the student model. It seems like there's a maximum amount of information the model can learn from these hard negatives before it starts to degrade. When we looked into why, the reason became obvious. The negatives were more relevant than the positive. It's now possible to have humans go and search over the entire corpus and exhaustively find every single possible relevant document. As a frame of reference, this is the size of Wikipedia. So it's obviously not possible for annotators to do an exhaustive search over the entire dataset for every single query. They're going to find some positives, but inevitably, there are going to be some correct documents or sentences in the dataset that they didn't find. And those our intelligent hard negative miner will find. So from there, we tried to find other methods, but it was clear that this method of triplet loss that everybody uses is just not the way. So instead, we thought about it and we came up with a completely new method. If you think about it, a query is a game that you have to play. All of the documents are trying to compete to be considered the most relevant, and we're trying to figure out which ones are the most relevant. And we have LLMs, which can go ahead and annotate this for us. One of the best ways to take a collection of candidates and figure out which ones are the best is ELO score. ELO is a simple yet powerful model for assigning scores to a set of items, assuming that the only thing you have are pairwise comparisons between those items. ELO has its first applications in chess competitions. For example, you would want to be able to assign global scores to all of the players that let you determine how good the different players are. However, the only thing you have are pairwise comparisons. So the way ELO works is that you first think of each player as starting with some default skill value of S. You look at the scores between the two players, and you look at who won the match. And you increase the score of the player who won, and you decrease the score of the player who lost. However, the number of points that you adjust their scores by depends on how surprising the result was. For example, if a weak player beats a much stronger player, then there's going to be a large transfer of points. Yet for similarly ranked players, the change in points is not going to be that high. If you take all of the pairwise comparisons and you run all of these score adjustments over a long period of time, all of the players will eventually resolve into a final score that you can then use to predict future matches. If you go on the leaderboard for LLMs, there's an arena, and that's based off of ELO scoring. Humans will go up, see a pair of LLMs, and pick which one they like more, but they won't know which one was which. This is the method that we brought into our reranker. You have a query, you have two documents, and LLM has to decide which one it prefers. In fact, we can even use an ensemble of many LLMs to get a very strong signal of which document is more relevant. All we have to do then is inference all of the pairs of all of the documents, then we run it into the Bradley-Terry formula, and out comes ELO scores for everything. Now, the model that we need to train just needs to take in a query, a document, and output an ELO score. And just like that, we're immediately able to distinguish all the fine nuance in all of the different documents. This type of nuance is hard to detect in other re-rankers, but our re-ranker, which is powered by all these pairwise comparisons, is able to easily distinguish them and give a higher ELO score to the correct, more relevant document. The final result is the state-of-the-art re-ranker. The results really speak for themselves. Whether you're evaluating domain-specific data, or languages that are not English, or very subtle nuances in meaning, or even queries that require instruction following, our ZRank model series are state-of-the-art models that handle all of that. You can try it at ZeroEntropy.dev.